Today, we're diving deep into the fascinating realm of sorting algorithms. Specifically, we're going to unravel the mystery behind one of the most efficient and straightforward sorting techniques. Now, let me introduce to you the brilliant minds who will guide you through this algorithmic adventure. First off, we have Giancarlo and Nathan who will be your guides in explaining the intricacies of the counting sort algorithm. For step-by-step visualization, we've got me and Rafael who will help you understand how the algorithm works visually. To break down the complexity analysis, we've got Ryan Lester who will shed light on the efficiency and performance aspects of the counting sort. And last but not the least, Angelica and Reina will take you through the Java code implementation so you can see how to put this algorithm into practice.
Counting sort is not a comparison-based sorting algorithm like quicksort or merge sort. Instead, it is a non-comparative integer sorting algorithm that works well with you have a limited range of input values. It is efficient when the range of input values, the difference between the maximum and the minimum values, is not significantly greater than the number of elements to be sorted.
Here's how counting sorts work. Counting. First, it counts the frequency of each unique element in the input array and stores these counts in an auxiliary array called the count array. Each index in the count array represents an element from the input array, and the value at that index is the number of times that element appears in the input. Cumulative count. Then it calculates the cumulative count of element in the count array. This step helps determine the correct position of each element in the sorted output. Build the sorted array. Using the cumulative count information, counting sort places each element from the input array into its correct position into the output array. It works by iterating through the input array, finding the count of the current element, decrementing the count in the count array, and placing the element in the output array at the correct position.
This is the array that we're going to be using. The initial step in applying counting sort involves determining the starting index for each number. The first task in this process is to tally the occurrences of each number within the array. For example, in this case, there is only one occurrence of 0 and 3 occurrences of 1. Thus, we record this as 1 and 3 respectively. Similarly, there are 2 occurrences of 3 and 0 occurrences of 2. These numbers can be stored in an array of length 4. Once we have these counts, the next step is to accumulate the numbers to the right. To illustrate, the number at index 0 remains unchanged, while the number at index 1 becomes 1 plus 3 resulting in 4, and so on. After this step, we have the sequence 1, 4, 4, and 6, representing the numbers 0, 1, 2, and 3. Subsequently, we shift the entire array to the right by one cell, examining it from right to left. Starting with the last index, in this case index 3, the value there should match what's currently in index 2, which is 4. We repeat this process for index 2 and index 1. Finally, at index 0, we place 0. These numbers, 0, 1, 4, and 4, serve as the starting indices for the respective number ranges in this particular example.
Once we have determined the starting index for each number, the subsequent process becomes relatively straightforward. To begin, we create a new array with the same length as the original array, which in this case has a length of 6. Next, we iterate through the original array one element at a time. When examining the first element, which happens to be 1, we determine its designated index based on the constructed array. Since the starting index is 1, we place this number into index 1 of the new array. Following this, we increment the starting index to 2. This ensures that when we encounter the second occurrence of the number 1, we know it should go to index 2 instead of 1. We continue this process for each number in the array, proceeding from left to right until we reach the final number in the original array.
Counting sort algorithm has a time complexity of big O of n plus k, where n is the number of elements in the input array and k is the range of input values. It is the difference between the maximum and minimum in values. When k is relatively small compared to n, counting sort algorithm can be very efficient, often outperforming comparison-based sorting algorithms like quicksort and merge sort. Counting sort algorithm has a space complexity of big O of k, where k is the range of input values. The space complexity depends on the size of the count array, which is proportional to the range of input values. When the range is small, this algorithm is memory efficient.
Concerning the class definition and counting sort implementation's constructor, they look very similar to other sorting algorithms. However, this time, we cannot make the class generic as the counting sort algorithm cannot be used on any type of object but only on integers. Therefore, the array passed to the constructor or the array we want sorted will be restricted to an array of integers. For the sort open close parenthesis method, you can choose to pass the minimum and maximum values as arguments to it, or you can retrieve them yourself using a simple min open close parenthesis or max open close parenthesis function. In our case, we will be going with the latter to keep our method definition as concise as possible. Inside the sort method, we went ahead and retrieved the minimum and maximum values using the Streams API max open close parenthesis and min open close parenthesis functions. Now that our minimum and maximum are calculated, we can start with the actual algorithm. The first thing we did in our example was create the array that will store the occurrences of each of the values present in the array we want to sort. This is done using the new keyword. The number of elements this array should hold is max minus min plus 1. Next, we want to iterate over the array we need to sort, and for each value stored inside this array, we have to subtract the minimum from it. The result of this subtraction, as we already mentioned, is the index referencing the slot in the array we just created.
The value stored or referenced by this index, which should be 0 when we start iterating, has to be incremented for each element we calculated. Now, after the number of occurrences, what we have to do is loop over the newly created array, storing these occurrences, and this of course is done using a for loop, starting at 0 and going all the way till max minus min plus 1, which is the maximum length of the array. Now, while the number of occurrences stored inside each slot is still different or bigger than 0, we have to store the index referencing the slot inside the initial array in its final stored position. However, before storing it, we have to add the minimum to it. As to create this index, we previously subtracted the minimum from the value we had. Of course, the number of occurrences will then have to be decremented, or we would be creating an infinite while loop. Additionally, the initial array index counter we created will have to be incremented. This allows us to store the next integer we iterate on, next to the one we just stored. And there we have it, the counting sort algorithm. Let's create a main method and test what we just implemented. In this method, I went ahead and created an array holding integers. As you can see, I also printed out the initial state of this array, how these integers are placed inside the array before we perform any kind of sorting. After we call the sort method and print the resulting array to the console, you can see that the array is now sorted in ascending order. If you wanted to store the array in descending order, all you have to do is reverse the direction of the second for loop, the one that is iterating over the newly created array, storing the number of occurrences, as you can see in front of you.